simulation scenario that highlights how the agent resonance integral influences the agent's response to environmental adjustments. This will allow us to observe how the agent's emotional identities interact with the sensory expressions within the environment and how these dynamics evolve over time. Here's the step-by-step simulation scenario outline. Simulation scenario, agent resonance impact. Scenario setup. Agent 1, mild sensitivity, emotional baseline, calm, stable, emotional response style, gradual measured, initial HRV 60 milliseconds, initial GSR 0.7 MUSs, initial emotional probabilities, P anxiety or equals 0.6 or 0.4. Agent 2, severe sensitivity, emotional baseline, prone to volatility, emotional response style, rapid intense, initial HRV 45 milliseconds, initial GSR 0.9 MUSs, initial emotional probabilities, 0.8. Step-by-step process. 1. Initialize agent profiles. Set the agent's baseline emotional states, HRV and GSR. Define the emotional profiles, mild and severe sensitivities, with different baseline emotional states and response styles. 2. Emotional vector and entropy calculation. Calculate the initial emotional vector, VIC, for each agent based on HRV and GSR. Compute the entropy change, frac DEET, for both agents, accounting for any divergence in the emotional vector field. 3. Calculate sensitivity and recalibration, agent sensitivity profile. Compute the physiological sensitivity factors, A, HRV, and GSR, based on the agent's HRV and GSR values. Adjust the calibration factor, gamma, based on entropy, frac DSD. 4. Environmental adjustments, sensory expression. Modify the environment using the updated phase shifts. Lighting, FOD. Sound. The intensity of these changes is modulated by the agent's emotional state and resonance. Emotional shift, impact on emotional probabilities. Based on the environmental adjustments, calculate the changes in emotional probabilities, particularly anxiety and stress. Update the emotional probabilities, P anxiety T, P stress T for both agents. 6. Calculate agent resonance integral. Use the agent resonance integral to evaluate how well the environment's sensory adjustments align with each agent's emotional signature, PI. High resonance means the agent feels aligned with the environment, leading to a calming response. Low resonance means the agent feels disconnected or overwhelmed, requiring further adjustments. 7. Update digital physiology. The changes in environmental phase shifts will influence the agent's HRV and GSR. Update HRV and GSR based on how the agent's emotional state evolves in response to the environmental changes. 8. Time progression. Repeat this process over multiple.
Absolutely. Let's bring this to life, step by step. I've got the initial parameters locked in. It's fascinating to see the subtle differences in their baselines, especially how Agent 2 starts with a lower HRV and higher GSR, immediately signaling a more stressed physiological state. Let's calculate the initial emotional vectors, VEC I _ 0, for both agents at T equals 0. Agent 1, mild sensitivity. I _
This is my
coherence
intent
1,
sim.
0 equals
Quantifying
frac
emotions and
HRV
stress and
_ 1, 0, 100 equals frac 60, 100 equals 0.6.